Today we're going to be talking about colligative properties. What are colligative properties? Colligative properties are properties that depend on the quantity of solute, not the identity of the solute. So it wouldn't matter what solute I was using. I could be using sugar. I could be using like antifreeze. I could be using all sorts of molecules. So I could pick out a bunch of different solutes, and it wouldn't matter which one, it just matters how much. And so the colligative properties we'll be talking about are freezing point depression, boiling point elevation, and osmotic pressure. So when we talk about freezing point depression and boiling point elevation, we're really talking about the solution's freezing point or the solution's boiling point compared to the pure solvent. And so those solute molecules that are part of the solution, they are interfering with the solvent molecule's intermolecular forces. And we need those solvent molecules to form really tight intermolecular forces or to break intermolecular forces apart when they're changing phase. And so the phase change of boiling and phase change of freezing really involves the intermolecular forces between solvent molecules. And these solute molecules, or solute ions, depending on what you're dissolving, are going to interfere with those solvent molecules changing phase. And so solutions will boil at a higher temperature than the pure solvent, and solutions will freeze at a lower temperature than the pure solvent. And so these are things that we've observed in real life. So you might be familiar that on roads in winter, they often put sand or salt on the roads. And this isn't just for traction, this actually melts the ice. And that's because the freezing point has dropped. And that means it's going to be liquid until a much lower temperature. And so the outside temperature is not cold enough to keep that ice as a solid. We've also seen some boiling point elevation, but this one's not quite as drastic or noticeable because usually we don't add enough salt to make it noticeable. So when you boil water and you add salt to it, mostly you're adding that salt for flavor, but it does increase the boiling point very slightly. Very slightly. At the end of today's lecture, you can actually work out exactly what the temperature of that water is. And so you'll be able to calculate how hot that boiling water is now that it's a solution of salt water. Also, a pro tip, if you're trying to cool drinks for a party, use salt water. The salt water will have a much lower freezing point, and so you'll be able to cool your beverages faster. So how exactly can we calculate how much our freezing point is depressed or how much our boiling point is elevated? Well, we have these equations here that will help us calculate just how much it's changed. So we have to remember this delta symbol here from when we had our delta T. Delta means change in. And so delta TF means our change in freezing point. And then M is our molality. And Kf is a freezing point depression constant. So we're going to be looking up Kf on a table. And so on Alex, that may mean that you need to open up the data tab in order to access the Kf and Kb values. If you would need them on an exam, they would be provided to you. Additionally, here is the equation for boiling point elevation, and you can see that it's very similar. The only difference is that this is a Kb now, and so that's a different constant. That is the boiling point elevation constant. But again, you'd look it up and it would be given to you on an exam if you needed one. Now, this is a note for our class since we are using Alex for homework. We're going to be focusing on problems where we don't have to worry about the number of ions. So for your exams and when we're doing practice problems in lecture, we will only encounter non-electrolyte solutes. But on Alex, you will encounter some strong electrolyte solutes. But that only changes things slightly. So when you're calculating your molality, you have to remember that strong electrolytes completely ionize in solution. So the definition of strong electrolytes are completely ionized. And so in order to look and identify if it's a strong electrolyte, you'll look for strong acids, strong bases on your green sheet, or soluble ionic salts. And so here's an example. This is calcium hydroxide. And when that ionizes, that's going to split apart into one calcium ion and two hydroxide ions because of that subscript 2. And so when I'm calculating my molality we have to remember is moles of solute per kilogram of solvent. And so since I have 3 moles of ions, then that's going to be 3 per however many kilograms there are. I don't know how many kilograms there are in this particular problem, but I would know that there's 3 moles of solute for my molality. Okay, here's an example problem, and we'll read it and then work it out together. It says simple syrup is used in many recipes. Simple syrup is made by mixing equal parts sugar and water and bringing the solution to boil. What is the boiling point of a simple syrup solution made by mixing 1 cup of granulated sugar and 1 cup of water? And then I'm told that 1 cup of granulated sugar weighs 198 grams. And then I'm also told that the molar mass of sugar is 342.29 grams per mole. And I'm told that 1 cup of water is 235 milliliters. Feel free to pause the video at any point if you want to work it out on your own. Okay, so I'm asked to find the new freezing point. And so that means I'm going to need to know how much my freezing point is elevated. And so this is molality. Molality, the definition is moles of solute per kilogram of solvent. And so that means I need to find my moles of solute and I need to find kilograms of solvent. And then I can plug it in to my equation. So I have to read back in the problem. And so the water is going to keep its phase and then sugar is going to dissolve. So since sugar dissolves, that is my solute. And water is going to keep its phase, and so that means it's the solvent. And so that means I have to get my grams into moles. And so when we find our moles of solute, I have to start with my 198 grams of sugar. And I have to convert that into moles. That must be why I was given the molar mass of sugar. Sugar's molar mass will help us convert between the units of grams and moles. I will need to cancel out my grams and I will need to get into moles. That molar mass means that there's 342.29 grams in every 1 mole of sugar. And so I can type that into my calculator. Follow along with your calculator to make sure you're typing into your calculator correctly. And you should get 0.578456 moles. And then I'll go ahead and track my sig figs. There should be 3 significant figures because of the grams. Next, I need to find my kilograms of solvent. And so to do that, I have to start with my 235 milliliters of water. And I need to convert that into kilograms. Now, we haven't done this for a while, but density is your conversion factor to go from a volume unit into a mass unit. And so I need the density of water in order to go from a volume unit to a mass unit. I need to cancel out my milliliters and I need to get to grams. That 1.00 belongs to the grams, and I can always divide a number by 1 because anything divided by 1 is just itself. Next, I need to cancel out my grams and I need to get to kilograms. The definition of the kilo prefix is 10 to the 3rd power, which is 1,000. So I can type that into my calculator. I get 235 times 1.00 divided by 1,000. And you should end up with 0.235 kilograms. So now I can calculate my molality. I'm going to do that up here because I don't have a lot of space. So my molality will be equal to 0.578456 moles with 3 sig figs divided by 0.235 kilograms. And that just had 3 sig figs. And so that is, type that into my calculator, I got 2.4615 moles per kilogram, which is the same as writing 2.46 molal. And so I could just write my unit as molal. So when I'm calculating my delta TB, I can use my delta TB equation And delta TB is equal to my molality of 2.4615 molal with 3 sig figs times my boiling point elevation constant. And so that is 0.512 degrees Celsius per molal. And so my molals cancel out, and then I'll be left with a delta T in Celsius. And that is 1.26 degrees Celsius. But I'm not done with the problem yet, because this asks me for what is the boiling point. It doesn't ask me for what's the change in the boiling point. It asks me for the new boiling point. And so I also need to know what temperature water normally boils at. Pure water boils at 100 degrees Celsius. That is the definition of the Celsius scale. That water, pure water, freezes at 0 and boils at 100. Now, since boiling point is elevated, I have to add my change in temperature to that. So this is the original boiling point. And then I'm adding my change in boiling point. And so that's 101.26 degrees Celsius. Now, how many sig figs you have really depends on how many sig figs you have in that original boiling point temperature. And so I'm trying to remember what I have in my typed math underneath. But I'm just going to write it as 101.26 degrees Celsius. You can always look up the original boiling point, like on a data table. So if you click that button on Alex, you would find the original boiling points. So there is typed math underneath here. And so far we're all good and correct. Yay! All right, here's a practice problem for you. I'll read it and then you can pause the video in order to work it out on your own. It says ethylene glycol, which has a chemical formula of C2H6O6, is commonly known as antifreeze for use in automotive cooling systems. What is the freezing point of a 1.7 molal aqueous ethylene glycol solution? We're told the equation for the freezing point depression, and we're told that the freezing point depression constant Kf for H2O is 1.86 degrees Celsius per molal. Pause the video and try to work it out on your own. Okay, you have an answer. Let's work it out together and see if you got what I got. So we are told the molality, which is great. And so we just have to plug that in to our equation. So our delta TF is equal to 1.7 molal. And then we have to plug in our Kf value, which is 1.86 degrees Celsius per molal. 1.7 times 1.86. And so that tells us that my freezing point is going to change by 3.162 degrees Celsius. But I'm not done with the problem yet. I still have to calculate what is the freezing point. Water, pure water freezes at 0 degrees Celsius. So pure water freezes. So I'm going to write freezing point is equal to 0 degrees Celsius. So the next thing I have to do is I have to find my new freezing point. My new freezing point will be equal to my freezing point, original freezing point, minus my change in freezing point. And so I have to subtract those two numbers, 0 minus 3.162. And so my new freezing point of the solution will be equal to negative 3.162 degrees Celsius. Okay, so that was pure water's freezing point, by the way. And then we subtract the change in to find the freezing point of the solution. Go to the next slide. Okay, our last colligative property is osmosis. Osmosis is really important for biological systems. And so if you take a biology class, you'll learn more about osmosis. Osmosis is the flow of solvent from a less concentrated solution to a more concentrated solution. Solutions are separated by a semi-permeable membrane. So there's our semi-permeable membrane separating our two containers. And so since one side contains sucrose and this side contains no sucrose, then our water is going to be flowing this way into the sucrose side. Because from the water's perspective, there's not enough water over there. And so it's flowing that direction. Now, if you increase the amount of water on that side, then it's going to go up in volume. So volume increases. On the side, they had higher solute concentration. Now, since that side increases in volume, there's more weight of the solution on that side. And eventually, that extra solution is going to weigh so much that it's going to stop the flow. It's like, I can't flow anymore. So that's going to push back and prevent water from continuing to flow into that side. And so we say that this side has the higher osmotic pressure. All right, here's a practice problem to see if you understood the previous slide. It reads, a semi-permeable membrane separates a 10% starch solution from a 5% starch solution. The 10% starch solution is labeled A, and the 5% starch solution is labeled B. Fill in the blanks of the statements below. Solution blank has the greater osmotic pressure. If you answered A, you are correct. Let's sketch that out. So we have our two solutions. We have solution A, we have solution B. Solution A is 10%, solution B is 5%, and solution A is more concentrated, and so it would have the higher osmotic pressure. Pause the video and see if you can identify the answers to number 2 and number 3. Okay, let's check your answers. And so it says water initially flows from blank into blank. So since we're flowing from the less concentrated side to the more concentrated side, we're going to be water's going to be flowing from B to A. Now, since water is leaving the B side and going into the A side, the volume of A would increase and the volume of B would decrease. And so the level of solution B would be lower. The biological example of this is regarding blood cells. And so I have pictures of 3 red blood cells here under different solution conditions. And so an isotonic solution, iso is a prefix that means the same. And so iso means the same, like isosceles triangle has 2 equal sides. And so those 2 sides are the same. And so an isotonic solution means that the outside solution, outside the cell, has the same osmotic pressure as inside the cell. And so there's no change, there's no flow in or out of the cell from the water molecules surrounding the cells. And that's what you want. That is normal. But there are conditions where you're not normal anymore. And so a hypotonic solution has a lower osmotic pressure. And so what happens is that since we have a lower osmotic pressure there, then we do have water flowing across that cell membrane. And so we have to remember the hypo, we had some polyatomic ions that say hypo. Hypo means without. And so it's like without salt or something. And so you're going to be flowing water across the cell. And similarly, in reverse, a hypertonic solution has a higher osmotic pressure than the red blood cells. And so if you're in a hypertonic solution, you have crenation in your cells. All right, so I hope you enjoyed this mini lecture on colligative properties.